All right. Thank you, folks, for joining us on time. Welcome to the Research Connection Speaker Series. My name is G, and I serve as the Research Engagement Manager at the Autodesk Tech Center in Boston. Today's presentation explores how human AI collaboration can address one of the most pressing challenges in industrialized construction, producing small, highly customized building orders without generating excessive material waste or incurring high production costs. Dr. Pingbo Tang is an associate professor at Carnegie Mellon University, whose research centers on human AI collaboration for resilient infrastructure systems and intelligent building production. His work, supported by NSF, DOE, and the Manufacturing Future Institute, addresses the unique challenges of small batch, high customization construction, focusing on how AI and digital twins can reduce waste, stabilize production, and improve communication between design, engineering, and fabrication teams. He has led transformative studies in modular construction, civil infrastructure operations, and operator training through simulation and process mining. And without further delay, I will hand it off to you, Dr. Tang.
Yeah, thank you. Thank you, G. Thank you, everyone. Also special thanks to Autodesk for giving me this opportunity to present the work to a network of excellent colleagues working with Autodesk. I'm going to show you sorry. Yeah, I would like to acknowledge the support from the funding agency and also my industry partner, DMI company, and Modular, who is doing modular construction work in Pittsburgh area. And of course, my research team with Professor Yori and Professor Buju and a number of PhD student researchers. The challenge we're looking at here is called customization versus industrialization. We know Katira, it's a big company a while ago, and they attract a lot of investment, but still facing big challenges of cost escalation. One of the things I heard, maybe someone from your from the audience could help me know more about it. It's like, is this really the difference between the electronical manufacturing industry versus civil engineering? Because the direct CEO of Katira seems like it's from the electrical manufacturing industry, and that industry is not having such kind of like a very small order like what we have here. Like every house is different and has a very high customization because every people want to have a little bit of change of their house layout and the designs. And the barriers, it's become significant if we want to scale them up. If we want to handle a lot of order, and each order is not like a very standardized, and there is always some tiny change. How much cost we are going to make it affordable for the business to run and to make it profitable. So that's the question I keep asking myself, small order, high customization. So I go to those industry and to looking for some information. Case one, it's a module factory in Pittsburgh. They are making those volumeric, I hope my pronunciation is correct, the room modules. And the other one, it's the DMI company, one of the major HVAC system manufacturing company in Pittsburgh. They're producing the ductworks and also the connectors of ductworks for ventilation system. So when I facing those companies, when I went to their factory, I realized that this is not just individual manufacturing because they have the unique design at the very beginning. The architecture make the design, and the designer is going to engineer need to hand over the information to the engineer, and the engineer need to also coordinate with the prefabrication to make those fabrication process like a doable and with the existing machine. Then between the designers, there is mechanical system designer, architecture designer, structure designers, and all of them, they need to collaborate. They cannot just say, okay, I want to change the layout of the room without worry about the mechanical system, the ventilation system. Then all those interactions between the designers, engineers, and the prefabrication stakeholders make a lot of those change, and those communication, it's a sequential loop. It's a big loop. Usually, once you make a design change and you are not expecting they are going to give you all the information back within a month. We know we have those digital technology which can make the communication much, much faster, but we're still facing a challenge in that a lot of those pieces of our work is coupling with each other. We are not confident to hand over my work to another person without a comprehensive information. For example, the designer may not want to hand over like a 30% finished design to the engineer to start their work because they feel like, okay, if I give you this 30% of the information, then it's very, very likely I'm going to ask you to redo or rework on something after I make some tiny change of my design. Then those force people to do sequential collaboration, and the concurrent engineering in civil engineering is very, very rare. And it's not like some of those industry like textile production producing the clothes and the soft like a soft material. Then it's a multidisciplinary case, and it make us to facing a lot of those design engineering problem. But at the same time, even we just look at the manufacturing, we have those changeovers, very, very small order. And we need to set up the machine between those orders, say, okay, I produce product A, then I need to produce product B. Then we need to reconfigure the machine to make sure that we're producing the product to meet the specification. Then sometimes customize the product is very rare, and we rely on the worker's experience to set up the machine and look at how many possible combinations we can have for this ventilation ductwork production line. It's a connector production line, and it has a four parameter. It's only four, right? One is the like the size. The second one is the bundle size. The third one is the material, and the fourth one is the how long is the stick. Then with these four possible attribute, and you can change their variable. And for the first one, you have two possibility. The second one have seven possibility. That means if someone make an order, it's possible one out of these 784 possible combination. And some of them, they are very popular, and some of them, they are not that popular. For those not very popular one, that's problematic. We tracing the the production process, and we look into those standardized product and the not very standardized product, and we see that the setup issues for customized product, like not a very popular product, it's generating 36.2% of the scraps. Like the setup issues. Setup issues means we set it up and we commissioning the machine and produce, and we find out, okay, it's not exactly what we want, and we need to adjust the parameter of the machine, and it's called trial and error process. A few trial and error processes rely on the worker's experience. For Pingbo, maybe take like a day to configure the machine, but maybe for G and very smart can take once or twice. Then, but still produce waste. So 1/3 of the material. 1/3 of the time, which means we have to stop the machine and to check the machine and to reconfigure the machine. So that amount of time actually is significant for the factory. Now we are wondering, okay, we want to set up the machine and we need to handle so many changeovers with those customized orders in our industry for civil engineers, for mechanical engineer working for civil engineering project. Then we're looking at the efficiency, cost, and quality of our production process. And we do not have some data for real orders to help us to set up the machine automatically. And even the most experienced worker need to try and errors and to find out how to set up the machine correctly. The other one is the quality checking. And sometimes if the quality checking failed, they need to rework. And that also relying on inexplicit human knowledge. There is some automation of a quality checking, like a computer vision, but still in this industry, I saw on site is like they are still using those caliber and to have the worker to manually touch the product to do quality checking for these ductworks. The challenge here is that we are looking for a needle in the sea. If we set up the machine, and the machine might have a multiple process parameter, and each parameter has a few possible value, and the combination of those values could be significantly large. And we ask the computer to randomly sample the configuration space of a production line, which is a very simple production, only has 4 stations. And uh, and the random generation, 6 out of 50,000 samples generated, it's only like less than 1%. It's less than even like a 0.5%, right? Those are valid configuration for producing the product to meet the specification. So we're searching a solution in a very large space. Then we realized that if we have computer to search such kind of things in an even larger space to handle different customized requirement of a special type of order, then it's even more difficult. But surprisingly, we find out like the worker who even have no college degree in the factory, they don't know too much about physics and engineering, and they still have a pretty good sense based on what they see and what they saw every day. And even they never handle a new order or customized order before, relying on some of those tacit knowledge they had accumulated based on their work experience in the factory before. They have some kind of good heuristics to explore the configuration space. And the computers can do massive data collection and analysis, but the computers does not have that heuristics. And the computers does not have the capability of a worker of reasoning under conditions of uncertainty and incomplete data, which is very complete for civil engineers. We get like 80% of the design, or we get 80% of the engineering information. We have to start to think about what we do. But human also has a limitation. Of course, human may not reach like a very unlimited memory, and human might get fatigue, and the human might not be able to scale up their reasoning to a large network. But computer can if computer know the rules. Then we're looking at a combination of the capability of human and computer instead of have computer to consume a lot of data. And we are very, very curious about human data. What I mean by human data, we just want to get more information about the behavior of the worker and when they are facing customized orders. We have the computer to observing a different situation, like a different type of order, and the machine set up found by our experienced worker. And we also tracing the observation behavior and data analysis behavior and action behavior of set up the machine of a worker in the factory, and to find out, are we able to explain their tacit knowledge based on their behavior? Sometimes those workers know what they're doing. Sometimes it's very difficult for them to explain some of those details. It's like we are asking Michael Phelps to explain why Michael Phelps is swimming faster than someone else. Then we need to have some AI to observing human behavior, and we want to have the computer to analyze those behaviors and to find even better solutions compare what human has been doing. So that means we want to have some kind of like a superhuman. Superhuman means if we have experiences from multiple people explained by the computer, then are we able to combine their experiences and make them reusable and to enhancing the performance of other people? So this is the key. We are looking at the interaction between human and the machine and the computer system to capturing the tacit knowledge from human system process during the changeover. And we also have the performance captured, like how much waste has been happening and how many trials and errors done by this worker. The cost, in our case, it's the number of cycles of trial and errors when someone is handling a changeover. And we also want to set up the goal to say we do not want to have too much trial and errors because that's waste. Every time we try, produce, and the produced material does not meet the specification, that's a waste. Then we want to reduce those. Then we want to we do not want the computer to produce something random, and we need some physics-based knowledge. So those physics-based knowledge is coded in the process model about the manufacturing line. There's some physics rules and we have to follow. We cannot completely rely on statistics of the document or some kind of like a behavior, statistical analysis of the behavior by itself, because that's not sometimes it should be regulated by equations of a physics production model. So once we have this challenge and we say human behavior should be a key component of this overall picture, I'm not saying the other research studies about optimization AI is not useful. It's very, very important. I just would like to bring those blue pieces into the picture and to see how it could contribute and helping the other pieces. To integrate the human behaviors into this big picture has a lot of challenge. Number one, even those humans know what they're doing, and but explaining their behavior, it's very, very difficult because there are so many different type of words they're going to use to explain, okay, I'm doing this because of this. And there are many, many different wording about the relationship between what they're doing versus the factors influencing what they're doing. Then once the computer remember those human behaviors, it does not mean it can interpret those behaviors, because we need a formal or standardized coding system to coding what they're doing is a process pattern. It's a similar thing and for similar concept and similar relationship. So those on domain ontology usually has been hard coded by a person, like someone is going to formalize the domain knowledge with a concept and the relationships. However, in this real production line, in this industry, I realized that there is a lot of those variation of the domain ontology used by different group of people. For example, the designers and engineer and the manufacturer, they may all say, okay, this is a door, but the definition of the door and the focus of the concept of door is different. For example, the structure engineer, they focus on the frame of the door, and the architecture designer, they focus on the opening of the door. Then that makes those communication between different stakeholders very hard, and also harvesting the human explanation about what they're doing and why they're doing this very difficult. And I highlighted a few things here and to call for your help, because I know many of you know but much better than me. If the computer want to explain human behavior, sometimes there is a new concept, like somebody even do not formally define something as a new concept, say, okay, I see a lot of people has been doing this for a long time, but I don't know what is that, how to define that thing, right? Then we got to updating your domain ontology to incorporate those similar things happening frequently again and again in human explanation using some kind of different wording, but it seems like it's the same thing. But what I hope is a dynamic domain ontology, not a static. And we want to have the human data, human explanation to enrich our ontology in a dynamic way and to handle different stakeholders' opinion about those concepts and relationship. So that's a dream. And we got to start with somewhere, right? And I start to use a large language model. And I started coding some internal industry knowledge library from their inspection manual and from their maintenance history. Then what we are trying to do is like we collecting some of those descriptions from those manuals. We suppose they have some kind of domain knowledge and to reflect those physics-based principles they are relying on to make the decision. And so those physics-based relationship, it's usually it's a equation or differential equation to regulating the production process. But sometimes it's very hard to find those equations, and we take a step back and to say, okay, if we cannot find the equation, then we still should be able to find some causal relationship between what they're describing as one concept influence the other concept, and to coding them into internal industrial knowledge library. Then we ask the operator to be able to use our RAG system. I think this is very popular now, retrieval augmented generation system, to searching and to query those internal knowledge library, and also to have the human behavior coded as well to say, okay, how this person has been doing things in the real workspace versus how this person has queried our library and to make the decisions and to allow those human query response process and human cognitive behaviors to be integrated into this large number of documented production process, and to help us to explain why this person is asking this question and why this person is doing this in the workspace. And we create a navigation system to allow the worker to understand in the past, someone has been doing this before and why they're doing this based on the records in the inspection report and based on the maintenance report and based on physics-based knowledge. So the first step should be we need to tracing human behavior in the workspace. And we are looking at the integration of computer eye tracking technology and computer vision technology to tracing human observation sequence when before they set up the machine for handling a unique order. And this is a very experienced worker, and he is observing different parts of the machine before start the production. And the network on the top right, it's a sequential observation of different parts of the machine has been capturing his attention transferring process before they start to set up the machine and do the work. Then during that time, it's a think aloud process. Think aloud means we ask this person to say, I observe this because of what? It's a think aloud and use audio recognition to generating some kind of explanation. We did some kind of like a comparison over this human and AI and to justify why we need to learn from this person. You can see this picture and for the same machine. And we set up the like a trial and error platform for human to try to do things to set up the machine and to produce the quality product that meet the specification. As a human, based on a human's intuition, takes less than 50 steps, this blue line, to find the right configuration. It's just human intuition. And for the orange line and the green line, that's a Bayesian optimization and reinforcement learning. And it takes a few hundred steps. And we run the algorithm multiple times and with the same starting point. And we see that human, the blue region shows that the variation, and the orange also show the variation. Those variations is significantly different. Human is more reliable, and even for multiple runs, multiple sessions, the variance is not as big as the algorithm. Then we think we should have human navigation, and we have machine to follow up, because human seems like has the heuristics to be able to find some good things and to use their domain knowledge to have some basic judgment before they search all the combinations. Then the algorithm can follow up and to say, okay, I have this human knowledge domain and to capture based on their behavior. And the computer can assess their behavior and to summarize their behavior to optimize their behavior. Then with this, we call this is a type of like a digital twin, because we think the digital twin should be operational and should not be like a duplication of a real world only. It's a duplication, but it also should capturing the operational process of the production process. Then where those knowledge should come from, because the operational knowledge and the causal relationship, we tried a few things to get it from this human observation process. The first type of thing we are trying to do is to integrate the human observation trajectory on that machine to guiding the algorithm to set up the machine. So that observation trajectory without a specific object information, it's not really a knowledge integration, because that's why we call implicit knowledge integration. We just say, okay, they look at here with XYZ, look at there with XYZ, without knowing what they're looking at. And the strategy two is we tell them, okay, the algorithm, no, they are looking at check the bubble quality, check the seal quality. Those are the meaningful semantic information and underlying those XYZ of the eyeball movement. Integrating these two type of like a human behavior to guide in the machine produce significantly different outcomes. If we do implicit, we can see that it's helpful compared with that blue bubble on the left side, right? No human knowledge integration. It's a very like a highly fluctuation of the performance and spend a lot of 200, 400, 600 steps to do the things. And if we have implicit human knowledge integration, it's very interesting. We only just tell them, okay, look at this first, and just step one. Then the machine's variation significantly drop to this orange bubble. But if you have explicit human knowledge integration with one human step, it can have the explanation and also has the first step guided by human say, I'm looking at this. It's already a good guidance for the machine to reduce their variation. And we also see that the comparison between human and AI is significant. You can see, even with the human-machine collaboration, explicit knowledge integration, out of 100 times of computation between a human and the reinforced, I think it's Bayesian optimization algorithm, the algorithm with the human guidance still only can win 41 times with the help from the one step of human knowledge. And we are trying to do like a multi-step of human AI collaboration with the knowledge guidance from human and the machine do one thing and the human guidance again and the machine do another one. I hope it's going to make this 41 larger. At least we need to achieve 50, right? 50-50 means like a human and a machine is equal. Then we have been doing similar work for material handling. And I mean, a lot of you has been doing like 3D printing or carbon fiber material handling. And we apply similar process to observing how human handle the material and to reduce, to make sure that the shape of the produced material, it's follow a complicated shape. And what we noticed that it's like only experienced worker can handle very complicated shapes to make the carbon fiber layer by layer and to form the specific shape. And we use a process simulation algorithm to explore the human strategies of handling material, use their hand, and to find out why human hand can do better job than robotic arm. And we also try to remember the trajectory of a human hands moving and to integrate the trajectory of a human hands moving with the computer algorithm. And what we find is very interesting. We find out that like if we have the human gestures to guiding the machine, the quality out of these three quality criteria, like a quality on this slide, fold, sharing, weight, wrinkled area, those percentage has to be small. I mean, larger means a bad because there is more low quality or defective regions. And we can see on the right side, if we have those algorithm trained with a human behavior, and it has a significantly lower percentage of defective regions for this all three category of defect. I'm going to use the last 15 minutes to introduce a very related work because this is Autodesk. I'm using Revit to do this work, and it's a very like a human and AI collaboration, which is not a modular construction, but it's about inspection. We look at the physical environment, and we also want to understand why human inspection in this physical environment are so different. Like every bridge inspector, they have different behavior, and how their behavior could inform machine learning and artificial intelligence agent to do better job. On the other side, we want the artificial intelligence and machine learning to help the human realize that what they're doing is more leading to a more reliable bridge condition assessment. Then it's called human-cyber environmental interaction to guiding both have human to stabilize the bridge inspection behavior and also have AI to learn from human to do a comprehensive crack search of a bridge. The problem here is that we have a good national database, but within this database, the condition assessment of bridges seems like it's not as detailed as what we want, because at the end of the day, we do not just want the bridge to say, okay, it's a good condition, medium condition, bad condition. We want to know what exactly the bridge has the problem and what is the safety level and how likely the bridge will collapse, right? Then with those rating system so far, we do find out there is some kind of like interesting variation across regions. And it might be many, many reasons for the national bridge inventory showed us here. If you look at Ohio, Pennsylvania, those numbers, 9 means it's a good bridge. Every point here is a bridge. It's a state bridge, interstate bridge. And the red means like condition is very bad. It's almost close to, it's closed. 0 means closed. It could be many, many reasons to show this kind of like a clear border between state, but I'm not going to conclude it's based on human behavior. Maybe organization factor, financial factor, resource allocation, all can contribute to this, or based on the age of those bridges by themselves. And from here, we can see those interesting patterns, and we want to know more about why those patterns show up. And we found out an article from 2004, and someone has been doing like a bridge inspection reliability analysis. What they're saying is like 95% of condition ratings are questionable. I have to be clear, it's not like they are making mistakes. It's like when they're estimating the bridge condition as 5, then it's plus minus 2. If it's out of plus minus 2, they're going to say it's questionable, right? And sometimes for those bridges, which is good, like if you have a new bridge, you say 7. 7 is plus minus 2, like it's a 5 to 9. But for some of those bridges who is like a 4, then it's questionable and it's dangerous. A lot of those cases, don't worry about this 95. Just focus on like how reliable is a human to judge the condition of a bridge. And for good bridges, it doesn't matter. For like a bridges on the boundary, so that's the risky situation. So that those risky situations may not exceed a huge number yet, but after a few years, maybe after 10 years, we're going to see more and more bridge getting to 50 years old, 60 years old, then we need to pay more attention to this number. Then once we look at this, we need to understand the human behavior. And we check the observation behavior of a transportation engineering student and a structural engineering student. Basically, we're tracing their eyeball movement when they are doing a bridge inspection experiment using Revit. And we import our finite element model simulation results about the color of the internal forces of a bridge, which has a defect. We simulate the defect by reduce the stiffness of a bridge component, and then to use a finite element modeling software called ANSYS to simulate the internal forces given those stiffness reduction for some of those bridge components to simulate the cracks. Then we ask the student to use Revit and tracing their mouse movement and their eye movement, and to understand what they are looking for when they are trying to find out the weak part of the bridge. The transportation engineering student focus more on the middle of the screen. And like the structural engineering student, they actually have some intention to look at the middle of the spans. Seems like the knowledge of them, their learning is effective. Now, we want to understand more about the difference between those different people has different background. Then we designed the Revit-based bridge inspection game and applied to 100 students. And we try to explain their behavior and using some coding system to say, okay, what type of things they are looking first before they move on to find the next crack, and how that's going to help them to find more cracks with less steps. Then once we have that, we should be able to transfer the bridge inspection knowledge based on the behavior analysis. Then this is the software we're using. We have this like a Revit as the platform to help us do logging. So that's why I should explain things to Autodesk. I really appreciate Autodesk has this platform have us to logging human behavior, like their mouse movement, and to mine their observation, like a mouse movement and the button click process and the rotation of the model within the environment. And we mine those histories and to understand human behavior. Then we can see the causal discovery from this. This is from like a Revit, I believe. This is from Revit, and we look at the Revit dynamic label bar, right? And we mining those logging and to explain human behavior. And we also ask the person to explain why they're doing this. Then the goal is we want to have this large language model combined with a physics-based model from ANSYS and also using the human behavior captured in Revit and to explain why some people are more efficient in finding the weaker part of the bridge. And are we able to have the large language model to help us to accumulate the knowledge based on the analysis of many, many people's inspection behavior? The coding system, I could not elaborate because we don't have enough time, and I only have 45 minutes. But I can give you a very overall explanation. We are looking for type level information. We cannot just say, okay, I look at the bridge component A, B, C, which is instance. We're looking for what type of bridge component someone observed first. Then they move on to another type of component. Are they connected or not? So those are like a type level, class level information, not instance level, so that we can make it like a template to accumulate bridge inspection knowledge to say, I look at this type of things first, and I look at that type of thing, and that will form a good strategy for searching for cracks. Then this is the type information we're looking for. We classify bridge component into three types, like a both end pinned, one end fixed, and the other one pinned, and both end fixed. So the question is, when somebody is looking at a certain part of a bridge, and we classify them into one out of these three. And on top of that, we also classify them based on the level of momentum, sharing level, and the torsion level. And at the component level, we also tracing when they are looking at the top, bottom, left, or right of the box girder of the bridge. So that coding system actually gave us a lot of interesting observation when we do the experiment with 100 students at Carnegie Mellon. We find out people don't want to pay too much attention to both end pen because it looks like there is not that high a risk if you have both end pinned. It's like there's less axial forces of that component. But if you see there is a one end fixed or both end fixed, a lot of people like to look at that because their domain, their structural engineering professor told them there is this axial forces and you need to pay attention. And some of those forces is going to transfer from the neighborhood. Then for the component level, and we see that there is this transferring process pattern. And if one end is fixed and the other one is pinned, then there's a very high probability people are going to jump in between these two type of bridge component. And if the sharing level and the moment level is very high, they also have very high, it's 89% of the jumping probability. Then we look into those explanation. We ask the person who played the game to write down where you find the crack and what's your explanation of this crack. Then we try to mapping what they write down versus their behavior. It's very interesting. We find out some of those inspection behavior it's always correlated to diagonal crack and the sharing forces. So that's their conclusion. And we are still looking into a more reliable algorithm to summarizing those inspection behavior. And the goal is to say, if we analyze the behavior of some people who are observing a particular bridge. In the future, if there is a similar behavior show up, we are going to remind this person to say, a lot of people has this behavior before. They diagnose the condition of the structure as diagonal crack and shearing forces. Are you sure? And the co-pilot might be able to use that historical behavior data to inform the inspector and helping them to be more comprehensively searching cracks. So this is the last slide, not last slide, and this is the overall picture we are looking for the future. We want to have a middleware to explain human behavior and the artificial intelligence algorithms data analytic capability to combine cyber environment and the physical environment to support more reliable inspection of structure and other type of workers. This is the coming back to the modular construction industrialization. At the very beginning, we mentioned that architecture engineer and construction people, they work together, but they are looking at the same group of concept with a different focus of the attribute and the math attribute of those concepts. The designers might focus on some attribute of windows and bathrooms because they are more looking at the functions of those spaces and openings. The prefabrication, like a factory, they focus more on the material property, and they are going to focus on the collaboration between them. And sometimes their collaboration cycle could be very, very sequential and make those kind of communication process take a few weeks. And we don't want those a few weeks like a sequential communication. And we want to have a concurrent process graph. If Revit allow us to look into the communication or like interactions of between human and a Revit model. And what I hope is that we could find out some people who is focused on some part of the building, their work actually forming smaller groups, and they should not worry about, okay, I only have 30% of the whole building. Am I okay to sharing the information with the prefabrication engineer? In some cases, we should be able to trace in those relationship between the designs and the different parts of the design and the different parts of the manufacturing, and to find out, if possible, smaller groups should talk more frequently rather than have those huge building completed before they hand over to the manufacturing, so which takes weeks. Then the human behavior modeling should across individual human, across different stakeholder will help us to find out, are we able to do concurrent engineering, civil engineering? And this is the process. I hope that we could to use a platform like Autodesk having like a construction cloud, Revit, and some digital twin platform of Autodesk has been already doing, and to tracing the designers, engineers, and the construction general contractors' behavior to enable concurrent, at least partially, not completely. I know it's very difficult to do really concurrent engineering in civil engineering. Then we could develop those simulators to allow the designers and engineer work together and to tracing their behavior of design, tracing their behavior of engineering analysis, and to see to what extent we allow them to do concurrent work. At the end of the day, we want to go to the field, and we want to have a human to be supported by the information from the production line, from the field, and also from the worker's behavior from the past, and allow the worker to reuse the experience and to get the support from the AI to enable them to optimize past experience and make a superhuman. And that superhuman will helping one person to facing a unique situation, and that person, their heuristic still going to be their unique decision. It's not replaced by AI, but the AI use the historical data to help this person to make a better decision in a unique new situation. Thank you.
Thank you so much. We'll open it up for questions. I really appreciated how you framed the whole presentation around like a very multidisciplinary lens. And I thought it was fascinating how like the researchers and students are subconsciously impacted from the disciplines they're coming from, especially when you were tracking them working in the virtual realm. So yeah, I found that fascinating. Brandon, please come
Thank
off
you.
mute.
Yeah, hey Pingbo, great to see you again.
Thank you, Brandon.
Yeah, there's some content there that I didn't get to see when I was visiting, related to the bridge.
Yeah.
Um, could you share some insight into the I guess maybe the importance of the gamification of that, like of the research exercise that you had the 100 students
Mhm.
conducting? Because I feel like something like this is, you know, widely applicable in other ways, and at least in how we experiment with producing prototypes and getting them in front of customers and whatnot. Like, do we need to, you know, should we consider this more like gamification approach on like introducing it to them in a way that is, you know, is more accessible from an experience point of view? So I'm curious if you could just share more about how this went about going on.
Yeah, yeah, very good point, Brandon. I'm not a UX person. I know a lot of my student who is doing that. Right now, there is one human-computer interaction student in my lab, and he is tracing the user interface interaction, and to see how somebody is using. In his case, it's not Revit. It's a software to control a nuclear power plant and to ensure like a safe operation and to I I'm not a UX person, but I'm sure that if we gamify this have a gamification of like a bridge inspection or the designer's user interface. Maybe we should trace their design behavior using different layout of the interface and to see which functions are more. I think that's already you guys must be the expert. You're doing much better job than me. You don't need to ask me, right? Yeah, to see which part has been used and which part are not used and which part has correlation with each other and how those layout of the user interface create more streamlined design experience. I don't know.
No, it's interesting to hear. Thank you.
Yeah.
Any other questions? I have one. You mentioned like at the institution level, how some of the data informing their research stems from manuals and like physics-informed learning models, some
Yeah.
operational recordings, and also the group studies like this one. Can you speak a little bit more about the data gaps that you see currently existing, particularly when you're trying to apply it directly to industry applications?
Um, yeah, that's a very good question. I can use this yeah, human behavior data is certainly missing because
Yeah.
we do not see anybody who is collecting like the attention transferring process when someone is trying to set up the machine. But it doesn't mean non-human data is perfect. Non-human data, for example, in our case, for this manufacturing line we're looking at here, you can see this is the physical factory. They are collecting the data at the end, not at the beginning, or that like they have some sensors to measure how many fin half finished product has been gone through different workstation. But I don't think they have like a progressive quality checking. And some of those quality problem, when you find it, is already too late. And they have the worker to randomly walk over and pick up something in the middle and to see what's the problem. And that's a manual process because there's no like a people talk about computer vision to observing the surface quality. Then, but I don't know why they are not using it. I don't know why. Maybe you guys know it. And that they do not do progressive quality checking,
Mm.
and it produce a lot of like a too late regret, like material is already wasted. That's a few things I observed. I think the quality checking is a
Mm.
low-hanging fruit for us to get some progressive data about the production.
Mm.
Yeah,
Thank you.
yeah.
Any other questions before we wrap up? Otherwise, Dr. Tang, thank you so much for that informative presentation. I know a lot of folks wanted to join who messaged me to share the recording with them, so I will make sure to do that
Thank you.
and share it with the broader audience on our YouTube channel. But yeah, thank you everyone for your time, and yeah, please feel free to reach out with any questions. And Dr. Tang, we hope to stay in touch with you in the future.
Thank you. Thank you very much. Have a
Yeah.
good one. Okay, bye.
Thank you, everyone.
Bye.